is the matter of the microstructure of matter, and our first speaker is Sir Harry Kroto, who is known worldwide as one of the discoverers of the fullerene molecule. The fullerene molecule as a geometrical structure was known long ago, but as a molecule made of carbon atoms was discovered by him and his colleagues in 1985 at the Rice University, for which they have got the Nobel Prize in 2006, if I remember well. He is now...
Too well.
He is now professor at the Florida State University and also the University of Sussex in the United Kingdom.
Okay, thank you. I'm just checking how many were in my lecture last week. Yes, okay, I got one new joke, so sorry about that. Hope you might even notice it. Okay, well, it's about symmetry, and a lot of the stuff that I do involves art and graphics. So basically, we're just going to look at things that I think are interesting from a symmetric point of view. And the first thing is you only have to look around this room, and what you see are these objects and the curtains, okay, and the patterns on the chairs, where actually what you've got are the same pattern repeated, okay? So there's something very deep in sort of the animal, just animals as well. We're all animals, but not just human beings. And one of my favorite images is this one of Jacob Bronowski, who was a very eminent scientist and wrote a fantastic book, The Ascent of Man, and made a whole series of programs for the BBC. And here he's playing with his grandson, and the grandson is actually learning already something about symmetry by taking a cube, as you see here, and presumably putting it through the square hole. Now, there was one little child who shall be nameless, who every time he picked up a shape, he tried to force it through the round hole, okay? And it doesn't matter what the shape was, the little kid wanted to put it through the round hole. Cube, pyramid, sphere, whatever. And his mother decided that he wasn't going to get to the TUD, Technische Universität Delft, or whatever it is, and decided to take the child to see a psychiatrist. And the psychiatrist said, basically, don't worry, I can analyze this child. It doesn't matter what the problem is, they only see one solution. There's a perfect career for this child, and that's to be a politician. Okay. Mrs. Blair. Okay, so basically, this is it, and it goes deep, and these are objects. I presume that they are actually from that 4,000 years old, and they are really the Platonic structures. Okay, they have the same symmetry as the Platonic structures. And colleague Alan Mackay thinks that these were things for wrapping twine on. Okay, so if you actually, now this is a possibility, they were actually useful. So this perhaps was, if it is true, is the first and probably the only use of symmetry where you get something useful out of it. All right, okay. If we go back to the first chemistry book of Plato, he says, in the first place it is clear to everyone that fire, earth, water, and air are bodies, and all bodies are solids, and all solids again are bounded by surfaces, and all rectilinear surfaces are composed of triangles. Now, I hope that is clear to everybody here, but not always clear to me. And of course, that was the basis of the Greek chemistry. They had only 4 elements: earth, fire, wind, and water. And in fact, if we look at the Korean flag, whoops, daisy. If I get out of that, I think it's here, we find that these symbols are earth, fire, well, that's heaven, so we'll call that wind and water. So again, these things are sort of involved in symmetry and involved in deeper aspects. Now, it seems to me that the fundamental thing is the face. And if you think about it, that the first thing that a child probably sees is a face of its mother. And so, if you think about it, they're actually developing their perception, their visual perception, from scratch. There's nothing in there, okay? Unless you're religious, you might think there's something in there, but basically there isn't anything in there. And finally, if you think about it, then that particular symmetry, it's CS symmetry. I made a mistake somewhere, I don't know why. But if we look at this, and this young woman was supposed to be perfect, all right, according to this advertisement. And so we'll have a look at that by basically taking left plus left, okay, if we go back, and right plus right, and it's not actually obvious that she is actually perfectly symmetric. And I think we see here that slight asymmetry, broken symmetry, is rather better than real symmetry. So that's the way it is. Also, when I was a child, I remember, well, I don't remember it fully, but there was no censorship, so my mother took me to see the Hunchback of Notre Dame, and I was so frightened I had hid down behind, because if that symmetry is too broken, it's very disturbing, okay? If it's only slight, it's actually interesting, because a rather famous model called Lauren Hutton was highly asymmetric, okay? If you see the two eyebrows there, and in fact you put left plus left and right plus, totally different face. And so here was one of the first supermodels. I mean, supermodels are beautiful, but don't do anything other than look beautiful, right? So a friend of ours is Kittai, the famous artist, and here again we see a dissymmetry in his self-portrait. Also, we see patterns that somehow many tribes, they paint their face. And in fact, we got that now. Tattooing is coming back and things of this nature, trying to add to the beauty of nature. One of my colleagues, again, slightly distorted with the mouth and gives that some sort of picture. And my wife is over here. And I actually do art and do have paintings and posters. And I'm just fascinated by the face. I'm also fascinated by these faces, and we see in animals a relationship with ourselves. And in fact, one of my favorite paintings is this one, and we see the face almost symmetric, and this gives it a power that it didn't have before. Okay, so these are other images. Okay, I quite like this one because you can actually just distort it and make it humorous. I mean, I don't know why this is funny, but basically this cow. And so we find interesting aspects. If we think about basically this, we see that basically as a face, probably because it's the first imprint of a symmetric pattern that's in our minds. And if one looks at the sort of brain receptors in, say, monkeys and people, we find that vertical lines trigger one receptor, horizontal lines another one, different shapes. And therefore it seems that our visual perception is a convolution of lots of symmetric patterns where all these receptors are going at the same time. Another favorite artist of ours whom we met was Follon, a Belgian artist, and I thought I'd show you this picture. Again, we see this head symmetric. I'm reading a book, and in fact my favorite picture, which Margaret took over here, where again there's some sort of symmetry in the whole thing. Again, when you do things in multiple images, things look as though they're interesting. Well, flowers are interesting too, because we know that some of them are quite symmetric, have symmetries in them, and it sort of suggests that as bees and flies go towards these, that the same sort of symmetric patterns must be imprinted in really simple animals as well. So there's something very deep. It's not just in human beings. And this guy obviously appreciates the sort of symmetry that we're involved with, so that you can see that it's not known. So multiple images have some charisma for us. A favorite of ours is the Der Rattenkönig in Basel. If you're in Basel, go to this museum, because this is quite an amazing sort of thing. Here we see the same object repeated, and because it's a symmetric pattern, it gives it some extra power. And to give you an idea, it's bloody big. So if you want to buy this, you want a big room to put it in, because it is quite enormous. And so it's quite interesting to think about seeing just one of them is something, but seeing a whole set of these, and then all tied by the tail, because I think that the Rattenkönig, the fairgrounds in Europe in the 15th and 16th century, they used to tie the rats' tails together as some sort of a humorous thing for people to think was humorous. I think we've now moved on and recognized tormenting animals is not what we should be doing, and we're transmitting our own love of our family and hopefully of other nations to animals as well. Okay. There's a museum, Guatelli Museum in Parma, which I think is really quite interesting. On the outside, you'll see everything. But in fact, when you see all these objects together, and these are just a few of these, he's taken all these shoes and he never threw anything away. He was a school teacher, and it's the Guatelli Museum in Parma. And I do advise you, I cannot do it justice in this talk. It's just an amazing set of rooms. Here, look at this. All the walls of these tools, you see on the right-hand side, you see hammers, okay? These are all farm implements in an enormous room tied to, again, multiple images. If you go here, these are all cans. In every single one of these, for instance, here we find razors, okay? Keys, corks, bobbins, all right? An amazing museum. Here you see there's some pattern here, round clock, rectangular clock all the way. This was in his bedroom, okay? I don't think any of these clocks were working even when he was alive, okay? Again, the whole house is full of these things, toys all on the wall, and again, the multiple imageries where that brings in some sort of symmetric aspects. Okay, so basically what is nanotechnology, which is to some extent what I'm involved with? It's actually putting things together and self-assembling into multiple objects. And these images, one by themselves, but as a pattern again, deep in our materials, we find symmetries and crystallographic structures. And one of the most famous images of nanotechnology, I think many of you will have seen, is this one. It's called a sort of nano coral, which again, the scientist, I think he's retired now, I forget his name's gone out of my mind, has made it into a symmetric pattern, which is reminiscent of one of the most famous photographs by Edgerton of a milk drop. And of course, these photographs showed us something we'd never seen before, that every time a drop falls down, this sort of beautiful dynamics occurs in this relatively symmetric pattern. And my favorite image is this one from the film Dr. Strangelove, which is the war room. And I think it comes up again. If we talk about symmetry historically, one of the most beautiful drawings, well, it was actually Piero della Francesca, and I think we're in an architecture room here, who designed this of the perfect sort of city. And we see, again, symmetry, slightly broken symmetry, not exactly the same on both sides. Again, the Parthenon, very famous. I think this is in South America. And of course, one of the most famous, which is Stonehenge. Okay, which goes down, say, 4,000 or 5,000 years. So symmetry is absolutely fundamental to almost everything that we do. If we look at the logos of, I think this is the chrysanthemum of the Emperor of Japan, and I think this is the, I forget what they call the logo of the first shogun. We go back to symmetry in Egypt, in Australia, and again, this image again. And this I'm not so sure about. I've just realized, because this is from my archive, what it says here is that this is something Dürer's pentilings. If this is correct, this is actually rather similar to Penrose tiling, okay? Which Penrose tiling in 2-dimension is related to the 3-dimensional tiling that Dan Shechtman got the Nobel Prize for. Alan Mackay took this and actually predicted the possibility of crystallographic structures from Penrose tiling, but I need to check this out, whether this actually is a Dürer pentiling. This particular one, if someone knows, is this from Dürer? If so, then it really...
the left side is...
The left side is. Well, that's the left side is not quite right. The right-hand side is very...
Not the original, but the reproduction.
Yeah. Okay, but the right-hand side is probably Penrose, yeah?
No, but it's Dura also.
It's Dura also, okay. So it should be Duratiling. Well, we Brits steal everything. Okay, there you go. I was in Rome and I just looked at this just see the power of the asymmetry. What made this, first of all, powerful was the fact that it was not a symmetric one, as the Egyptians. If you look at Egyptian sculptures, they tend to be highly symmetric. If we look at this is more, but what makes it powerful is that it's broken and that there's a sort of metal what is it, nail holding it together. So, okay, so well, let's think about where this all is involved. It's all involved in education. It's all involved in how we develop. And I thought, he says here, observation favors only the prepared mind. And so I need to think about education, that I was actually educated some time ago. But one of the things that I did do was a lot of drawings. And again, cars of the same CS symmetry. Actually, not all of these were symmetric, but this was one where I've taken Leonardo's famous Vitruvian Man and put him inside a buckyball. Okay, this is my great contribution. And also, when this was done, I wasn't transcribed by me. It was transcribed by the person who was doing the poster. And you notice that this guy's got an Achilles heel. There's no yellow on this particular thing. So I like to point out a slight dissymmetry there. These are some of the logos and posters and menus that I did. And this particular one is one of my favorites, where we have changed the Byzantine dome, which is actually related to a building in Brighton where this conference was held. So these are some of my drawings that you've seen before, and we'll come back to some. So that is part of my education. Photography, I also had a camera, and some of you will recognize that these are some of the things that you used to have to do to get a camera, to get a photograph. How many of you have done this? Let me just check. You'll remember what it was like to take a photograph, and it was quite a big exercise. I thought I'd remind you, and for those that have never done it, you will realize that life was more tricky in the old days. But you learned some chemistry. And this is just the negatives. You had to actually get the positives from those to get a picture. And it was quite a long exercise. And you had to have a good reason to do it. And I found one actually here, she's in the audience. But today, all the kids really need to do is this. Okay, that's all they do. And they've got a picture. It's instant gratification. And I think what has happened with technology is that has happened, and basically I'm sure it's going to have an impact on many people, okay, that they just want something very quickly and not prepared to work at it to get something that is of use to them. So that bothers me. I also had Meccano and made things. I like this, Meccano boys, and today we've got to add girls, of course. Our keen, ambitious, and inventive, no boy or girl who follows the Meccano hobby can be a bad boy or bad girl. But we had some children yesterday, and it was a 3-year-old was fantastic. I should have put the picture on. There was one 3-year-old who was making buckyballs yesterday in the square, and she came back to make some more. It wasn't just satisfied with making one. She came back with her older sister and told her older sister, who was about 6 years old, how to do it. So there's something interesting, because that's the youngest child that I think we've ever had in our workshop. So making things, again, we see here in this picture things that have symmetry, and I now use electrons to stick things together. However, it turns out that here was a Meccano football, and it says here, I hope you can read it, no doubt readers will find several possible uses for this novel sphere built by Mr. A.H. Finlay of County Down, but we do not consider that it would form a very suitable football. This is 1928. how wrong could they be? Okay, because if they patented it then, they would have had it. So there again, somehow we see symmetry. Oh, aligned and cut with colored paper and fitted with an electric lamp, the sphere would form a very pleasing decoration. Okay, well, not far out really, because in fact, if you're going to put these symmetrically round a sphere, you will have to use these functions of icosahedral symmetry if you're trying to do this symmetrically, if you look at any of these symmetric structures. I also collected things, images, and again you see your faces come through, a lot of them. And I used to do this because they were free. When I was a kid, I had no money, so I collected free stuff. All this is free artwork. I mean, and in those days, the cameras and the photography was a lot more complicated, and the art was very much involved. Great things like this. Again, Swinging London. So my favorite image of the sun is this one. And I've got a huge collection of images. Menus, I like this one. See how much more powerful it is by putting the two together. Okay? Again, this CS symmetry, the same as the face. And so these are some of the things that I collected. I collected things like cartoons as well. Then we win the Nobel Prize and get rich and go on talk shows. Okay. What about the babes? When do we get those? Okay, which is okay. Now, the other thing that I collected was a Graphist magazine, which is the major journal of graphic art. And I took it, this is my first ever issue, I think around 1958, 59. And then there are some other ones, again with the sun. But the most important one, which we'll come back to, is Graphist 132, Expo 67, where this was an image that was in there. And this was so striking for me, especially as it was in the nighttime, that I sort of was almost indelibly printed on my mind and was to come out later, fortune favoring the prepared mind. You never know how to do it. As far as architecture is concerned, I was really quite fascinated by architecture as well. And this is one of the drawings when I was about 13. This is Stockholm Town Hall. We see again a sort of symmetry involved. I drew this when I was 13, and this is where the Nobel Prize is awarded. And long before I knew what the Nobel Prize was, as a kid, it was just a very interesting building for me. Some symmetry at the University of Sussex, the Sagrada Familia, the Hong Kong Shanghai Bank, and something that I think is a fantastic building, which is this one, the Marin County Civic Center. And I thought I'd show you this. If you're in San Francisco, it's only about 20 minutes north of the Golden Gate Bridge. Every part of this image has symmetry in it, okay? If we look at this, we see these circles, we see the way that Frank Lloyd Wright has created symmetric patterns around it. And the most fantastic thing about this is, well, come in a second, again, the symmetry on the dome at the center. And for me, the most intriguing fact of this is that it's basically based on the Roman aqueducts. These are absolutely beautiful structures. And again, they get their power from the multiple production of the same structure, but also their usefulness. And it's interesting to to remember that Frank Lloyd Wright said, form and function are one. Now, I think one of the big problems in modern architecture is that basically people are building buildings just make them look either stupid or whatever they think, without thinking about whether what they're doing is actually going to be useful in the structure. And that causes a problem. Now, I like a lot of modern architecture, but I often go and think, well, what the hell is the point of that, other than someone thinks it looks pretty? And it's not always the same, because prettiness is in the mind of the beholder. Some people appreciate some things more than others. So that's another aspect. Again, symmetry in architecture, very, very famous ones. This fantastic building, and again, the Marin County Civic Center, which is actually in the film Gattaca. If you want to see this building, the whole of this film is filmed inside the Marin County Civic Center, which is open. You can just walk in it. It's a living building. You go up there, have breakfast there. Oh, this is another building which is famous. It's the iconic pavilion in Brighton. And when there was a conference on chemistry at Brighton, I designed this logo for it. Okay, and this is on the menu. Of course, the shape it cannot have that shape in a real flame, but the real flame will not have this inverted curvature. Okay, a real flame will just be, if you look at it, doesn't have that, well, whatever it is. Now this is an interesting dome, and the question is, why is it not a Buckminster Fuller dome where we see this symmetry? And the reason is that it would interfere with the radio signal. So it's deliberately made asymmetric so that it will not give an interference with the radar antenna on the inside, because any structure that has symmetry will cause problems in the detection. So it's deliberately made asymmetric. But of course, fundamentally, there are mathematical relationships that are needed here, but we also know that it's not really a Buckminster Fuller dome because not all of these are triangulated structures, okay, as we are here. We'll see that basically every one of these, okay, it will be of this kind, hexagonal or triangulated. And again, this particular magazine and this particular picture will come up again. Now, I must have been fascinated by this when I was a kid because I painted it 3 times, okay? All right, so here we see these, let's go to these elements. So bring them together, okay? Distort the symmetry, broken symmetry again, and then bring them together again like this. And this is a Maori pattern, which I must admit, as a child of about 12 or 13 or 14, I must have been fascinated by. It was on the most common stamp from New Zealand. All stamps from New Zealand that ever turned up in England, this must have been 9 pence, must have been the sort of international sort of stamp. And I painted this one size the size of a stamp. I'm not sure why I did that, because they already had the stamp, a load of them. And then one size about this page A4, and then one on a shield when I was at university. We had something that you had here where all these people went down the river yesterday. We had something similar where we didn't go have a river, we went down the road, and we all dressed up as stupid people, you know. But I had a shield and looking like an idiot with a shield and spear and stuff like that. But I used this particular one. I still have this shield at home. So it's interesting if we go back, because it's multiple elements. So let's take these away and then go back to this and realize that basically there's been a distortion of this symmetry. And then there's the yin and yang and the red and black, white as well. This very powerful colors, which a certain sort of group of people in 1930s actually used this same sort of color pattern for themselves. Bilateral symmetry is probably the most important. And we see the same thing here in this tortoise, but we see some other symmetries in there again, because it's actually fundamental to the bicycle, say, all right, to the stability or staying upright, or you're wobbling it a bit. And we saw the albatross at the beginning, and we see the pelican diving into the water. One of my favorite record covers by Roger Dean, based on this amazing aeroplane. Which is the fastest aeroplane. I think it went round the world in 4 hours. Okay, this is the fastest aeroplane that's ever been constructed. Okay, again we see a symmetry of this kind, which is the symmetry of almost all animals. All right, and there's a picture of my real favorite record cover by Roger Dean of, again, this amazing animal, the elephant flying with this CS symmetry. Flags also seem to very often be symmetric. Rather a well-known one around here. Okay, again related to this circular symmetry. And this is the image from Dr. Strangelove, and this is the war room. Okay, and have many of you seen Dr. Strangelove? Well, there's a great line in here because they're all arguing and shouting and almost fighting, and then I can't remember, it says, "No, you can't fight in here, this is the war room." All right, which is a rather nice line for it. The British flag is quite interesting because it's not quite symmetric. If you look at it, basically you can see this sort of symmetry. It's not as symmetric as you might think. But it's based on the flag of Ireland, but the Irish flag is made somewhat asymmetric, which gives it again that rather great extra power that the totally symmetric flag would not have. And here are some, I think this is a flag, not sure where, one of the states, I'm not sure. Hawaii. It's Hawaii, yeah. You see, Hawaii was never officially ceded to the USA. By the way, we still own Hawaii, but I think its possession is 99.999% of the thing. Okay. Anyway, there you go. Let's talk a bit about science, because science is full of these sorts of things as well. And language is the key to culture. And the question is, what is it? Mathematics. I talked about Hooke's law, but I want you to think about this again. What is Hooke's law? Because it's actually very close to everybody who's ever done any cooking. All right? Basically, the power of a spring is in the same proportion with the tension thereof. That is, 1 power stretch it or bend it 1 space, 2 will bend or stretch it 2, and 3 will stretch it 4. Now, that is Hooke's law. There's no equation in here. And I don't know who was the first person to actually write an equation of physics. Now, I'm not talking about an equation, because that goes back to India, the Greeks, actual equations, okay? Even Al-Khwarizmi, who wrote the book on algebra, in his book, there is no equation. It's all in words. He lays down the foundations of algebra based on Indian mathematics. So he took Indian mathematics, where some of these things were there, and then formalized it. But there are no equations in the book by Al-Khwarizmi. So basically that's it. And the problem is that integrating prose is not easy, okay? All right, it's rather difficult. I assure you it's fine. But however, an equation it's slightly easier to integrate this and get a half kx squared. And then produce what is the most beautiful curve. It's the parabola, okay? Which is basically the fundamental energy form, okay? And so in those equations, we see, if we can take them into a graphical form, we can see again these things. And I would argue that there was no science until the language of science was finally recognized, and that is mathematics and calculus, and that you have an ability to transform these things. Now, there was common sense, okay? There was that sort of. Now, as I pointed out, I think, common sense is not science. For instance, common sense tells us that the sun goes around the earth. That's common sense. It's science that looks into it a bit more detail, okay? All right, so there you go. Some of the parents of science, Tycho Brahe. And I want to show you what exquisite sort of equipment this guy had to determine the motions of the planets, okay? Just look at this. This is absolutely stunning. Even today, we can look at this and say, how did they do it with we have so sophisticated equipment, we could still do not see anything as beautiful as that. Kepler worked on this, and in fact, it is Kepler in this book who worked out his own logarithms, okay, to do the calculations. It's so easy to do calculations now with a computer, but this was an immense, immense task to determine basically the motions of the planets. Now, it turns out the most important thing that Kepler found out was that the motion of the Earth around the sun was not circular. The most important thing he discovered was that it was an ellipse with the sun at one focus. And it's not very far away from a circle. That, again, is broken symmetry of a kind. That discovery was the start of science. Now, there are no equations in Kepler. It may have been Christian Huygens, and I would like some of you guys to find out whether he has an equation. All right? I've not found it yet, but of course I've not been to, I guess he was in Amsterdam, or maybe he's also spent some time here in Delft, I don't know. However, whoever wrote the first equation of physics, okay, that means Hooke's law, physics, putting parameters which apply to physical things into the equation, that was the first physicist, the first theoretical physicist. And it could have been Christine Huygens. There is some claim to that, but I have not yet found it, okay? Let's see what he did know. First of all, he's on, I guess, one of your banknotes. He actually was the person who, the first wave theory of light. He had some of the first pendulums, and he knew this equation, but I haven't seen it written by him, okay, which is the equation of a pendulum. These are some of the other things that he studied, okay? He also apparently knew this equation, this of calculus, and had discussions with Leibniz, I think. But certainly Leibniz could write equations, okay? But I think it goes on. Newton on integration, basically it was all geometric. There are no equations in Principia. Okay, so when we get to all these things, basically, you can see here, I say that the ultimate ratios, which are inscribed figure A, K, blah, 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 we go back to this, okay, the trans-circumscribed figure, blah, 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 will have to one another our ratios of equality. And basically say, as the rectangles become thinner, the area of the inner rectangles and the outer rectangles will converge on the area under the curve, okay, which is integration. But that was known by Archimedes. Archimedes invented integration. He already knew that. But the differentiation was the key. Willems Gravesande. This is, how many of you know of this guy? Let me just check. Well, you ought to, because he's the most important person. He must be Dutch, something like that, around here. He said his chief contribution to physics involved an experiment where brass balls were dropped with varying velocity onto soft clay. His results were that the ball with twice the velocity of another would leave an indentation 4 times as deep. And and therefore what he's saying here, he says here, Monsieur Leibniz est le premier qui a avancé que la force d'un corps en mouvement n'est pas proportionnelle à sa vitesse, not proportional to the velocity, but as ordinarily sentiment, mais au carré de la vitesse, okay, the square of the force. Newton did not know that energy was mv squared. In fact, he thought it was momentum. It's Leibniz. And here was the guy, and it's Willems Gravesande, who did the experiment, got the evidence for this, okay. Leibniz, we know. Émilie de Châtelet corrected. I like this one, if some of you will know. Émilie de Châtelet translated Principia into French, and Voltaire, one of her lovers, wrote to Frederick II of Prussia to say that de Châtelet was a great man whose only fault was that she was a woman. All right, there you go. That's the way it was. Now, Feynman on mathematics.
If you're interested in the ultimate character of the physical world, the real world, and at the present time, the only way to understand that is through mathematical type of reasoning, that I don't think a person can without an understanding of mathematics. I think it's just, I don't know any other way to do it. We don't know any other way to describe it accurately and well, to see the interrelationships without it. So I don't think a person who hasn't developed some mathematical sense is capable of fully appreciating this aspect of the world. Don't misunderstand me. There are many, many aspects of the world that mathematics is unnecessary for, such as love, and which are very delightful and wonderful to appreciate and to awe and mysterious about. And I don't mean to say that the only thing in the world is physics, but you were talking about physics, and if that's what you're talking about, then to not know mathematics is a severe limitation in understanding the world.
Okay, so basically that's it. Let me take that on, put that down. Some kids appreciate mathematics more than others because they're prepared to use them on tattoos. Here we see an error in this particular Maxwell's equations, DNA, Heisenberg uncertainty, LSD, a sort of nanotube and a Möbius strip. And my favorite is this one, Nicole, a physics student. My tattoo is the Taylor expansion of sine. Again, we see symmetries. So we're going to the 3, 5, 7 because of the sine as opposed to the cosine and things which are squares in there. I consider it the most beautiful thing I've ever learned. It has additional meaning that is useful. All right. How many young people would say that about mathematics? And we actually met her, and we managed to get and anyway, there is Nicole. Now, why do I go to this, dy by dx equals k? I go to this equation, which is the fundamental one, and what we see here is JA times JB minus JB times JA is not equal to 0, okay? If these were 3 times 4, basically, and 4 times 3, and this fascinated me when I was at university, when I discovered this. 2 times 3 is equal to 6, 3 times 2. But in the quantum world, things can happen that are not so obvious. A times B is not equal to B times A. And if you want to understand spectroscopy, or to understand what's coming with the light from outer space, you really have to know this. And in this famous article by Van Vleck, okay, must have had some Dutch origin from this name, very famous sign. Practically everyone knows that the components of total angular momentum of the molecule relative to x, y, z fixed in space satisfy this commutation relationship. Now, when we arrived here at the railway station and everybody was getting off the train, I asked them all whether they knew this equation. And I tell you, nobody knew this equation. But I mean, the point is, however, this is the most important equation. Well, there are several of them, but this is a fantastically important equation, as I'm going to show you if I get to the end of this lecture. All right. Because it led to spectroscopy, which is what I was interested in. And if you blow this up, I look under a microscope, what you find again are some beautiful patterns where the molecule is actually making transitions. And this was my first ever result as a scientist. And it was a very, I would love it probably more than any other result that I ever got. All right, so there you go. To understand the symmetry here in these mathematics, they're fascinating. And again, just looking at it, empirical observation is not all. And one of the most important aspects of that equation is that if something is rotating, okay, to actually observe that and to see the dipole moment change, this is a negative and a positive charge, what one is seeing is that the negative and positive charge is moving up and down. And in an aerial that's transmitting to your mobile phone, the electrons are bumping up and down and giving out waves, okay, which you detect. So alternating electric vectors are what it's all about. Okay, so now I'm going to make sure I get you out of here in one piece. What I want to do is, yes, I'll go to this, as I've not got time to talk about everything I would like to say. I ended up doing radio astronomy, and yeah, I've heard that security alert here. This is the telescope that we used in Canada in the middle of summer, as you can see in this picture. We used this telescope, and what we detected is a molecule which is asymmetric, okay? There's a nitrogen on one end with a negative charge and a hydrogen on the other side which is more positively charged, and we can detect those. If that had a hydrogen, we couldn't detect it. It would not give out radiation. And we were able to detect these molecules in the space between the stars by their radio signals. As they rotated, they gave out radio waves. And here is a picture of when I used to have some hair. If you don't recognize him, this was, you might think it was me, but because I don't have any left. But then he never had any. That was, and we thought you'd show you. We were so excited by our discovery, got into the nuclear. So the chemicals were discovered thanks to Canadian work in radio astrology and research by the Celtics team. Okay, so there you go. Then what happened was that a star was discovered, IRC 10216, and I then, about this time, was interested in the chemistry of these stars and met Rick Smalley, who had vaporized aluminium and metals and silicon carbide by a laser. And I thought, well, if we vaporize graphite, we could probably make these carbon chain molecules that we detected in space and had been detected in stars. So basically, this is where you came from. That's the sort of star where all the carbon, nitrogen, oxygen in your body was made, and that star is blown up. That material all came out from the central star. You cannot see the star. It's shrouded, it's like to see the sun through a mist, okay? It's in there somewhere. This is forward scattering, and all this material is about the size of the solar system, is carbon, nitrogen, oxygen, and dust and stuff blown out, which then reforms in planets. And so this is your mother, okay? Basically, this is where you came from. So we simulated those conditions in a star like this one, again, material being blown out, and we detected these molecules with Jim Heath, Sean O'Brien, you and Lou. And here is the team, and basically what did we detect? We detected something that Leonardo da Vinci had drawn 500 years ago, that carbon can form a structure like that. But the question is, what about the proof? We surmised it had 60 carbon atoms, and we surmised that it had this structure. So the question was proving it. Well, the first thing that happened to me, I didn't know this, that you can tile a floor with squares, and you can tile it with hexagons, but you cannot tile the floor easily with pentagons. But David Jones in The New Scientist, I got this sent to me, showed that if you have 12 pentagons, you can close anything up, okay, as long as you've got 12 pentagons into a cage. So if we do this, basically add this, and on the backs we do the same thing again. Basically, I came up with what's called the pentagon isolation rule, and that for stability, all the pentagons have to be isolated. If you need 12 pentagons for isolation, 5 times 12 is 60. The first time you can do it is the soccer ball structure. You cannot make a soccer ball without 12 pentagons. Okay, so they had to be isolated. And at that point, I had one piece of evidence that we were right. Because I knew that if we go back to this, that structure in organic chemistry is unstable. So stability requires that 2 pentagons be isolated. Then, the major breakthrough for me was something very simple. I was like this little girl here, or like the little children outside on yesterday, making these models. And I played around with this, and I realized that I wondered if C60 was the first time that I could close the cage. It had to have 12 pentagons. Then when was the next time? And I found that if I had 62, I had to put 2 pentagons together. When I tried to make 64, I had to put 2 pentagons, and then click. Hang on. C70 is the second one. So I conjectured from this that if this is 60, this is a mass spectrum. So this is a species with 60 carbon atoms, that's one with 70. This is 62, 64, 66, and 68. I conjectured that 62, 64, 66, and 68 must have 2 pentagons side by side. And I rang up Schmaltz and Klein in Galveston, who I knew could do this sort of calculation, and on the phone, and he said, yeah, we've shown that it's impossible for 62, 64, 66, and we're halfway through 68, and I realized that this was a killer. If C60 was a soccer ball structure, then it demanded that the next one be C70. And I knew then that we had a solution which is very peculiar. 60 is a magic number, but 70 isn't a very magic number. It's a peculiar number. It's an asymmetric number. It's a broken symmetry number. So it turns out, basically, if you put 10 carbon atoms in between C60, you can make this structure. And at that point, I knew we were right, and I knew I wouldn't have to commit suicide. I was not on my colleagues would commit suicide, but me, that's another matter. Okay, so that was a great day. I want to go on because I've got a lot of things to say. Okay, let me go out because let me go back now to oh, here, first of all, I'll just go to this because we're running out of time. This is my sculpture of a giant buckyball, which is outside an institute in Sheffield. Okay, global warming is a hoax. What has symmetry got to do with that? Well, it has quite a lot to do with it. Because if we look at the HCl vibration, it has to have a dipole moment to interact with radiation. Okay? If we think of whoops, I think I got this the other way. I'm going to bring this down into this one. Go into the hydrogen vibration. As the 2 positive charge in the symmetric hydrogen molecule will not interact with the dipole. It's not a dipole interaction. It will be a secondary act, but it's very weak, Rayleigh scattering. So this is the first thing. To absorb the radiation, you need a dipole moment. Okay, so how has symmetry got to do with it? Well, carbon dioxide, which you've heard of, has actually got a symmetric vibration. There's no dipole moment change in this, okay? The charge is the same. What about the asymmetric stretching vibration? Okay, this one does. Now it becomes asymmetric. Okay, and it will have a dipole moment. The bending vibration is the same. Okay, so let's go through it. It will have a dipole moment. Okay, as this carbon there is positive and the oxygens are negative, the dipole moment will be plus to minus vertically. Okay, and if it moves to there, it will be plus to minus. So that can interact with the radiation. So symmetry is important. Okay, the carbon dioxide vibrations are the symmetric stretch, no dipole moment, no charge distribution. In the case of the asymmetric one, there is one, and in the bending frequency there is one. So if you look at the infrared absorption, okay, and now look at these whole things, we can actually get out of that, look at the vibrational spectrum, and here we have them again. And as the radiation comes in, it will set the bending vibration going. So the molecule will be sitting there, classical picture, not quite quantum, a bit more interesting. It will absorb the radiation. The symmetric vibration will not interact with the radiation, but the asymmetric stretching frequency will set it into oscillation. So that's the situation, and what is happening is that radiation is coming in, re-radiated in the infrared, and will set the CO2, and it will absorb in the greenhouse gas. Okay? And you know, as we said, some more about that. Okay, let's jump on. So I want to talk about a couple of other things before we go. What did this woman do? Probably the most important thing of all time. Here is her student talking about the experiment.
As a junior research student at the time, I was given the job of persuading a whole heap of Ransburg to lie down in an orderly fashion and try and get an X-ray diffraction photograph of them. Not getting a very clear picture, I went to Maurice Wilkins, who was looking at extracted DNA, and found that you could put it into fibers, so I used these fibers to make a specimen to give me a DNA pattern that I could compare with the Ransburg pattern. Of course, pulling fibers isn't quite as easy as it sounds. You take some of the pure material and put a little on the microscope slide, add just enough water to make gel, and then you can use a glass fiber stuck on the side of the microscope with a piece of plasticine, which you lower into the gel, and you need the lamp on the side to see the fibers, which when they come are very, very tiny indeed. It seems rather more difficult after 20 years than I in fact remembered.
Anyway, arguably the most important experiment ever done. Certainly the top 5. Okay, so what is it? Armand Lucas, good friend of mine, a little bit of the film that's on the page. Just let's start. If you want to see the whole film by Armand, it's on this Vega website. Vega, V-E-G-A, put it into Google, Vega Science, and you get it. Okay, so now he's going to tell you something very important about this.
The diffraction by the zinc, I think that's what the zinc great thing is. Of course, you can guess if you incline the line in the other direction, you are going to incline this line in the other direction. So there you are.
There's no prizes for guessing that.
No prize for guessing that. It's just symmetry. Now let's put the zinc and the zinc together. Of course, you get a cross, a Maltese cross. And so the diffraction pattern of the zigzag, if you have a polymer in the form of a zigzag, it has to be a cross. So the next picture is sine waves. And you can see that you still have a beautiful Maltese cross. And remember that the sine wave is the projection of the DNA backbone on the plane parallel to its axis.
Okay, now let's go to another bit of film.
So what you'll get is a cross like that. And the angle of the cross will depend on the angle of the helix. And when you went to King's with the erroneous structure Linus Pauling in his pocket, he was familiar with this X-ray diffraction theory.
Morris read it in his usual way, didn't convey sort of enthusiasm one way or the other, but I guess said yes, he didn't think Linus was the right structure. At the same time, however, he sort of let loose the bombshell, at least to me, was that actually there were two types of DNA X-ray photographs. There was the form which I knew about called the A form, which gave this crystalline pattern, But there was a second form called the B form. Opened a drawer, took out a photograph, and boy, there hardly believed. It was a perfect helix. It was a cross-like pattern, and he told me that repeated 34 angstroms, then it was a helix.
Let's stop it there. The prepared mind. Crick had already calculated the X-ray crystal patterns. You take X-rays and pass them to that little strand that he's trying to make, and you get the cross-like pattern. Now the crucial thing in this is there's a broken symmetry. You see that the cross is there, but there's one missing. And that's because there are two helices and there's destructive interference. So from that missing part, they could work out the separation of the two helices, how they were separated. The most important photograph of all time, this one, taken by, basically, in Rosalind Franklin's picture. Okay, let me go on because I want to finish off with a few things here. All right, we'll go here and go there. Okay, these are patterns. This fly knows something about soccer balls as well, because you can see there's a pentagon here, and there is another pentagon, and to close up, there's a pentagon there. Okay, so it's a fly with a soccer ball eyes. If we look at this tortoise, basically there's a pentagon right there. Again, to close up, it needs this. Viruses have this same icosahedral pattern. Artists love them as well. Dolphins like some broken symmetry, but we see here, again, symmetry in this particular object. This is so interesting. I got our younger son to create some characters, whereas Margaret and our older son writing this whole book, where a little boy and his dog, every time they see a pentagon, he gets 10 times smaller, and he thinks about this whole thing. This is actually published in Japan, so I don't expect all of you to be able to read this. He meets a frog, and they get inside the body, find viruses. So he sees a virus, he gets 10 times smaller, okay? Slides down DNA, and is then rescued by a buckyball that has been breathed in through the smoke of a person. And so we have this basically powers of 10, where each of these is a structure that one sees in nature, except for the soccer ball, which is the one that started it. Finally, key integers, 1, 3, and 5. Go back to this equation. In that equation is implicit the following, the whole of chemistry. Let's see what it is. All right. Basically, the Earth orbits the Sun. Use classical mechanics. An electron orbiting a nucleus, we have quantum mechanics. And according to that equation, that quantum mechanical equation, when there's an orientation, okay, there are 2j plus 1 orientations, okay. So when a quantum number is j, 0, 1, 2, and 3, that's a fairly well-known sequence, okay, there are 2j plus 1 orientations, okay, so when j is 0, 2j plus 1 is 1 orientation. When j is 1, 2j plus 1 is 3, there are 3 orientations of the spin, and when j is equal to 2, 2j plus 1 is 5, hence 1, 3, and 5, okay. Now I'm sure there are some physicists who can't do calculations, so I'll put some boxes in there for them. Right, now what I can do is double them up. Okay? Move that to there, move this to there. Double that, double that, double that. Move this to there and that to there. And what have we got? Periodic table. Explains the whole of chemistry, whole of life, and all the useful bits of physics, if any. Okay. And we chemists have to get back in physics. So basically that's it. And if you want to know how the modern world works, the mobile phone, computers, lasers, you have to know quantum mechanics. Not my fault. It's beautiful. It's actually very simple mathematics. Okay, it's not hard. It comes with these beautiful symmetric structures, the spherical harmonics, that tell us that the atom has electrons which have a distribution, if that's what you want, a physical distribution like that. Now, it turns out there was a book by Stephen Hawking, rather well known, and that book is called God Created the Integers. Now, that is what Euler said. Okay, some of you may know that. But I've just proven to you, basically, that the integers, the evidence indicates that, basically, the integers created God. That's my end of my talk. Thank you very much.
Thank you very much for this excellent presentation, and we have some time to put the questions to Sir Kroto. So you are free to put your questions. You can do question concerning this presentation, which had a very wide scope, and you can specialize your questions, focus on the full area as well.
Yesterday was played with.
Yeah, well, this is yes, you've done something naughty. Okay. I mean, basically, this structure is known, but not in I don't know, it's possible. You've got an 8 there, haven't you? But this is closely similar to a nanotube, so you can extend these. And the nanotubes are single molecules. This would be a nanotube if this were been surrounded by, but this was also possible structure. But there are thousands of these, and so that's a big problem. That's like, there you go. Nobody. They're all speechless. That's usually what I find. Yes.
So those molecules you saw originally, they must have condensed after the explosion.
Yeah.
How far do you think they were from when they appeared? How far were they?
The chain molecules.
Yeah.
The chain molecules. There was a lot of discussion about this because at the start of radio astronomy, they thought only small molecules would form because of the low density. It would be very difficult to make something with more than 2 or 3 atoms, and particularly 2 or 3 carbon atoms. So then, when this star was discovered in about 1980, they were discovered by infrared techniques, and then they looked at these with microwave, and they found our molecules coming out of them. So I conjectured that, in fact, the molecules were formed at the sort of second stage as the star was exploding. These are cool stars. So in the atmosphere of this star, we're getting a temperature which could be close to room temperature. Okay, and the density high enough for some sort of standard gas-phase temperature. And I conjectured that if we vaporize graphite in the presence of hydrogen and nitrogen, we would get our molecules, which is what we did. And so it was just a very simple experiment to try to simulate the conditions in that star. I didn't really have time to go into that. And what we found though, we got chains with 20 carbon atoms. So in fact now, chains with up to 11 and 13, and maybe even longer have been detected. And I am pretty convinced they're formed in a later phase as this star explodes. It cools down very rapidly. And in fact, even in supernova, you get molecules forming after about 50 days. So the temperature drops very rapidly, even in something as cataclysmic as a supernova. And in the gas phase, you can observe molecules which are very hot. But within 100 days, you're getting molecules formed in the outer atmospheres of these objects. So it's quite possible now. And of course, C60 has now been detected in these stars. I mean, that's on here. I thought maybe it should be. Can I find it? If it works, it's possible. I hadn't thought about showing this, but it's possible that it's in here somewhere. Yeah, it's here. This telescope, the Spitzer telescope, shown here, has detected C60. This white is the Spitzer sort of signal in the infrared, and the red is the signal that we get in the lab, and the blue is C70 related to that structure you just sent, this rugby structure, and we see that all the lines are there. And in fact, if we get out of that and then go to this, there's a horizon clip. This is Wolfgang Kretschmer, who was one of the 2 people who extracted this. But
I believe it is there, and it would be rather nice to feel that in fact we were on the right track. There are some interesting features in space, and C60 certainly can fit with any other proposal that's been made up to now. I'm a believer, and I think ultimately we'll find that it is there.
But others have said that C60 is nothing like a match for the kids in Nobel.
They're wrong.
okay, I'm pulling a little fast one on you, but they are wrong because they've not seen all the possible text. Oh, let me stop that. But the point is, quite an answer to your question, is that now, if I get out of that, go back, the amazing thing is that it gets the right one, which is this one. To show it again, I think this is really amazing that in those stars, in some of these stars, C60 is forming. So it's got to be high enough pressure to get 60 carbon atoms to come together. And of course, we know there's dust in space anyway. Why? I mean, 50% of all the solid, non-atomic material, or even more than that, is actually dust. So it's got to have got through a phase where you can actually form dust particles and form planets. I mean, here we are, something goes through this phase. So not only the change, but also C60 now. It's an amazing result. Okay, thank you.
May I have one more personal question to you?
Well, yeah, there's a lot of stuff.
There are rumors in the literature about those first days in early September '85. Microphone.
Oh.
So there are rumors in the literature about those first days in September.
It's too long.
Maybe this works?
It's not on. You have to shout. Okay.
Okay. So
I don't think it's on. And this isn't. This is just yours. Yeah.
So what happened since the recognition of the 70-60 to those days until you realized that
this is not working well.
To recognize that this is a spherical molecular intelligence. So I would like to hear your version, which is the most authentic version of the history of those first 3-4 days.
Well, you really want to hear. I mean, well, I haven't really dealt with those. Of course, it's the only authentic one. What else could it be? Because those of you who know Rashomon, how many of you know the film Rashomon? Yeah, so it's obviously my version, which is basically I went over there and to look for the carbon chains, and with Jim Heath and Sean O'Brien, with mainly then those Sean had actually constructed a new nozzle, which was very efficient in producing somewhat different results, and working with Jim Heath as well, and also a young student, we, after almost immediately, we saw this signal going up and down at C60, and I was interested in the smaller ones, okay? Basically, if we get out of this and, well, you're not plugged in anymore, okay? So you can just plug it in, and hopefully you are, oh, we are there, back there. If I go back to this, we got to the right, we need to go to this one, no, to this one. I use images as my icons to find my way around here. Rick had done this, is where we go to, this was the absolutely important structure here. And this is the birthday, this is the birth of C60, basically, on display. These are a mass spectrum, and here we see at 20, that's C10, 11, 12, 13 is weak. 11 is strong, 13, 14, 15 is strong. That pattern was known since the 60s. And I was interested in proving this, but during our experiments, we got this massive signal here, which said that forget those guys down there, I'm the king of the castle. And we were able to make the signal go up and down under control conditions. And that's why we decided that this was more interesting. And basically, I went to, my book was Graphis, where I had this image. And so I suggested we get Buckminster Fuller's book out of the library, and Rick went to get the book out of the library. What we didn't know that was the secret in this whole thing. There's only one pentagon on the whole of that you can find. There it is. Okay. It's hard. If you don't know it's there, you wouldn't even look at it. And that was a clue to the structure of C60. And then when we realized it's a soccer ball, we realized it must be good. And here is an image of this. And this is the Sussex group. So basically, I also had a structure at home of an icosahedron, which is, well, I don't know whether it is there, maybe not quite the right one, but let's pull this one down again just in case. I went to a restaurant, we went to a restaurant and we discuss what it, I don't know whether it's in the back of here, whether it might be down the back of here. No. Oh, here, so these are the two pictures which were crucial in my mind, and this one here. So we actually focused the laser beam and tried to simulate the conditions in a star, which is what you were asking about. That was C60, and then this is, I repeat this experiment. There's a load of stuff which is not necessarily in order. I'm sorry, this is all, okay, yeah, this is it. I also have this, I made a star dome for my children, and when we were discussing it at the restaurant, I said, well, you know, this star dome is not on, because it had been so many years before and I'd forgotten exactly what the structure was, that it also had pentagons. And that night, Rick constructed it, tried to make it out of hexagons, and found it would not close up. And when he remembered the pentagons, he said it did close up, and then he came in the morning, and this was a fantastic, it was 60 vertices. So we had discovered basically that we'd vaporized these structures. And then when we realized it was a football, we decided, you know, came out of the blue. And so basically that's it. Okay, and that's the birthday, 4th of September 1985. So that's roughly a rough idea of the basics of the story. Is that okay?
Okay, thank you very much.
Okay.
And thank you for